My name is Hastings Greer, and I am pleased to present the paper ICON, Learning Regular Maps Through Inverse Consistency. Many tasks in computer vision and medical imaging require finding the map that distorts one image to be similar to another. We demonstrate, symbolically and empirically, that as long as a neural network is required to produce such a map in an inverse consistent manner, then it will produce well-regularized diffeomorphisms, without any further smoothing needed. This is not a toy approach. Here, we train a network using our simple, one hyperparameter loss on the challenging OAI-NIES dataset. This dataset requires finding diffeomorphisms with large distortions while precisely aligning the thin cartilage layer to get a high dice score. We get state-of-the-art results, markedly better than daemons and in line with the highest performing neural network approaches. We begin with a definition of a diffeomorphism. A diffeomorphism is any map that is differentiable and has a differentiable inverse. Other methods of nonparametric image registration produce diffeomorphisms often by solving a fluid equation or integrating a velocity field, and in all cases using a complex combination of handcrafted smoothing kernels and penalties with several hypoparameters per term. We take a more direct approach by satisfying both terms of the definition. First, we have a neural network output a grid of displacement vectors and linearly interpolate between these vectors to find the displacement of any point in our image. This gives differentiability. Second, we require inverse consistency. That is, if you take two copies of our network, swap the inputs to one, denoted phi-BA, and compose the resulting maps, you get the identity. This is a much stronger condition than invertibility, since it requires that swapping the inputs explicitly constructs the inverse, but it is clearly sufficient. Therefore, assuming the network drives our loss to zero, it outputs a diffeomorphism. The question remains, why does it output a smooth diffeomorphism? It is clear why an inverse consistent map cannot fold onto itself, but it is not yet clear why it is smooth and appears to have the minimum distortion necessary to align the images. One hypothesis that jumped out to us was that there was something mysterious about training a neural network on a large collection of images that produce smoothness. Another possibility was that inverse consistency alone was sufficient for smoothness, with no neural network required. First, we proved by experiment that this isn't some statistical property of big data. Here, we train a neural network on a dataset consisting of a single pair of images, and we get a smooth transform. Second, we show that despite the dataset being optional, the network is needed. Directly optimizing the grid of vectors that define our map produces a map that is largely invertible, but non-smooth. Via these experiments and others, we narrow down the reason for the excellent quality of our registrations. Maps with large Jacobian, i.e. expansion or contraction, amplify any errors in inverse consistency. Therefore, if you penalize deviations from inverse consistency, in the presence of error, you also penalize deviations from a unit Jacobian. To understand this effect, we decompose a map into an idealized, actually inverse consistent term, combined with a noise term, i.e. jitter. When you apply our loss to a neural network that has been decomposed in that way, an implicit H1 regularization appears, penalizing the Jacobian of the map in proportion to the degree of noise or jitter. This explains the difference between the two experiments. The neural network output had some jitter due to the deep interconnections, causing this regularization effect to manifest, but the grid of vectors did not. This theoretical result implies a testable hypothesis. Adding jitter artificially to the grid of vectors experiment should smooth the resulting maps. This hypothesis is verified experimentally. When we add noise, we get the smoothness that we predicted. This provides evidence that the decomposition we performed in our proof accurately captures the dynamics of real training. In summary, inverse consistency is not just a term that relates to the semantic correctness of registration algorithms. It actually guarantees smoothness on its own whenever you are working with an approach that produces noisy maps.